One of the main issues with ML and DL deployment is finding the right way to train and operationalize the model within the company. Serverless approach for deep learning provides simple, scalable, affordable, yet reliable architecture. The challenge of this approach is to keep in mind certain limitations in CPU, GPU, and RAM, and organize training and inference of your model. This presentation will show how to utilize services like Amazon SageMaker, AWS Batch, AWS Fargate, AWS Lambda, and AWS Step Functions to organize deep learning workflows. Our speaker today is Rustem Feyzkhanov. If you could please correct me if I mispronounced it. Rustem is the author of the course and book Serverless Deep Learning with TensorFlow and AWS Lambda, and Practical Deep Learning on the Cloud. Rustem is a main contributor to open source repositories for serverless packages, Lambda packs, and step functions to processing. So please, I guess, introduce yourself further, and yeah.
Thank you very much for introduction, Ali. I'm very happy to present today. And today I want to tell you about usage of serverless infrastructure for machine learning pipelines. So let's start like why deep learning is actually important. So there is a market research brought by Data Bridge Market Research. So they announced that deep learning market will be $38 billion by 2027, and it will grow 34% every year. So it's pretty large. So a lot of companies try to use deep learning internally and externally, and it becomes more and more important for a lot of companies to implement deep learning applications. So today I will start with telling like about MLOps challenges with deep learning, which a lot of companies face. Next, I will tell like some words about like what is serverless and how it's organized. Next, I will tell like why actually there is why it's useful to use serverless for MLOps. Next, I will go more in detail and compare different serverless services. And finally, I will make an overview of serverless MLOps patterns. So first, let's take a look at how usual data science process looks like. First, we start with business understanding, where we try to gather requirements, understand data sources which we can use. Next, we acquire clean data. Next, we actually architect a model. After the model is trained, we operationalize it and put it into production. And finally, we get customer feedback. Actually, last three steps is a very iterative process. And we want to be able to get customer feedback as early as possible. At the same time, we want to be flexible in case we change any of our data sources or our model. And we also want to be able to integrate into production infrastructure. So serverless will helps to tackle these challenges. So a few words about serverless. Basically, in my case, I will cover like, so here you can see a spectrum of different ways of deploying your application. With on-premise, we control the whole stack from hardware to the code. With containers as a service, for example, we container everything from container and above. With functions as a service, we only control code. So in terms of serverless, I consider everything between CAS and FAS to be one, and I will explain more in detail. Basically, serverless means that you have on-demand cluster or worker or service, which will scale based on your consumption. You don't have any upfront costs. Pricing is probably pay as you go, and there is no payment for idle time. There is a small asterisk, which I will explain in more detail later. There is low operational support. It is defined as infrastructure as a code, so you can reuse different types of templates. And finally, there are built-in service integrations. So how it actually helps to solve the challenges I mentioned? Basically, because it has low operational support and no upfront costs, it's very easy to start using it in your startup or company to build first prototype or product. Because it's defined as infrastructure as a code and there are a lot of built-in service integrations, your infrastructure becomes very flexible, and it's very easy to change different services which you are using, different compute instance types, for example, and so on. And finally, it's scalable, and because of it has integrations, it can be used with your production infrastructure, and you can adhere to the requirements in terms of scale, time, and processing. So there are three main steps which need to be implemented when you want to build a deep learning pipeline. It's data preprocessing, training, and inference. With preprocessing, usually the challenge is that you have multiple sources and you have multiple data sources, you have different data. You may need to use different frameworks and libraries to process it. And you want to be able to process them in a scalable way. With training, usually you need to train and publish the model. The challenge here is that it's not as direct as usual software engineering, and there is a high level of uncertainty. And also you have to deal with high cost of GPU instances. And finally, inference or predictions. Basically, the challenge here is that usually it's the part which is integrated with production a lot, and you want it to be scalable, fast, and at the same time, you may need to implement some additional business logic. For example, when you deploy a new model, you don't want to deploy a new model to all customers because maybe it doesn't perform as well. You want to roll out to, for example, to 10% of customers, and then you want to see like if it performs better than the old one. So let's start looking into specific AWS services. Let's start with container as a service and function as a service. I call them serverless because, like, in a way, it's like serverless cluster because you just define code and launching configuration, and you don't have to manage how you scale the service. There are different services, and they have different scaling techniques. For example, AWS Batch works as a cluster, which will scale based on your job queue, where you submit jobs. With AWS Fargate and Amazon SageMaker, for example, they will start new VM for each job, so they won't have any cluster. And with AWS Lambda, it will start a new worker for each job. So let's start with AWS Batch. AWS Batch is basically is an on-demand cluster which will scale based on job queue. It has 4 components. Basically, job queue, which will have like separate jobs, job definition, where you need to define a job, and compute environment, which will start and terminate your instances. Next is AWS Fargate. Basically, it's container as a service which starts 1 VM per job. It can be used for both on-demand processing and as a scalable web server. And it can use only customizable CPU instances. So SageMaker has 2 services for running jobs. It's SageMaker processing jobs, which starts 1 VM per job, can be used only for on-demand processing, and limited to specific ML instance types. But the main advantage is that you can mount S3 buckets as disks, so you don't need to download or upload data in your code. With training jobs, it has even more advantages compared to processing jobs. It handles monitoring, high parameters, data import, and model export for you. And also it has support for spot instances, and it can handle checkpointing, aka saving your model after each epoch. And finally, AWS Lambda. AWS Lambda is a service which basically puts configuration, every time it receives an event, it creates a new container based on Lambda configuration and produces response. Every time it receives any new event, it will reuse existing container, which will be alive for some amount of time from 10 minutes to half an hour, and will produce an event. In this case, it will be a warm invocation. When it first creates container, it's a cold invocation. Cold invocations are usually slower than warm invocations. There is a big update based on reInvent 2020. So now you don't need to define Lambda configuration in terms of code libraries and so on. You can just have a Docker image and it will run on top of your Lambda. So that's a big thing. So now let's actually compare services together. Basically, if we put them in a spectral way, on one hand, you have something like AWS Lambda, which is very scalable, has very fast startup time, but it has certain limits. Or I would say it had certain limits because as was announced during previous week, now they have 6 vCPU limit and 10 gigabyte RAM limit. And now it has pricing per 1 millisecond, which makes it very attractive. On the other hand, we have AWS Batch, which basically has the most flexibility in terms of instance types which you can use. But you may need to pay for idle time because Serverless basically doesn't guarantee you 0 idle time. Remember the asterisk from the beginning of the presentation. And although it has like pricing per 1 second, the minimum is 1 minute. So if your job takes 30 seconds, it's still, you would pay for 1 minute. And SageMaker and Fargate, which are somewhat similar in terms of they're both containers as a service, they have medium startup time. SageMaker is more focused on running GPU jobs, although like it has CPU machines as well. And Fargate can only run CPU jobs. So next, let's take a look at basically the difference between using CPU and GPU for inference. The way I want to start like speaking about it is basically what are the requirements we actually need to have for inference. Usually, it's not just about speed. Usually, we also have to take into account cost and basically, and sometimes with inference, you have two types of inference. You can have an online inference, meaning you need to produce real-time response. You can have an offline inference where you just need to process a large amount of data. And also, we need to take into account scalability of our service. So if we compare different instance types and AWS Lambda in terms of inference time, cost per hour, and so on, basically, we can see that there is a lot of variation in terms of time and cost. Here, you can see the table, which is sorted by inference time from top to the bottom. So as you can see, Lambda has the slowest inference time. Here, I'm using Inception Web3 image classification model as an example. So here it has like 340 milliseconds. And on the bottom, we see inferential 1 instance, which has, I think, only 9 milliseconds, which is a lot faster. But at the same time, like we can see that there are cases where CPU performs slower, but CPU has somewhat cheaper inferences. But we can see that Lambda has basically very expensive inferences. But the thing here is that if we look at the right column, we will see that like whenever you start an instance, you have to pay for idle time also. And let's say you have instance for the whole month. For having 1 month of for example, inferential 1 instance, which I mentioned, you can have almost like 4 million inferences on AWS Lambda if you are using spot instance. If you're using on-demand inferential 1 instance, then it's like almost 15 million 15 million Lambda inferences. So basically, as you can see, if you don't have a lot of predictions per month, usually it could make sense to use Lambda. Now let's compare different services in terms of pricing. For similar configuration, we can compare Lambda, Fargate, and Batch. We can see that Lambda is almost 2 times more expensive than Fargate and Batch, and Fargate is somewhat more expensive than batch and significantly more expensive than batch spot. The thing here is basically with Lambda, you pay per 1 millisecond, and there is no minimal time. And with Fargate, you don't have any idle time. And with batch, even though like it's kind of the cheapest, you may still have some idle time when you have some cluster. For example, batch received some job. It started your cluster with one machine. It processed the job, and it won't kill a machine right away. When we compare GPU, we can see somewhat similar behavior. So SageMaker, which actually reduced prices, I think 2 months ago, up to 18%. So it's somewhat more expensive than batch, but at the same time, first it will like if you're using it for training, it will handle checkpointing for you. And second, with SageMaker, you can be sure that you don't have any idle time. And with batch, there may be a challenge that you have some idle time which you need to handle. Next, I want to cover like a more high-level way how you can organize your application. So usually when you, for example, with training, when you have your application, you usually try to put it on one machine and run it on one machine. And usually it's a GPU machine if you need to train the model. But actually, you don't need a GPU for the whole application. Usually you only need it for model training. But you have other steps in the process as well. And basically, you can use the most suitable services for other steps. For example, for data gathering, which is usually a very parallelizable process, you can use something like functions as a service. For data preprocessing, if you deal with large images or videos, you may need to use a multi-core CPU. And then when you want to upload a model, you can just run a simple CPU job. Basically, here we want to minimize GPU idle time. So we want to only, when we're using GPU machine, we only want to use it when we can train model in it. So to organize this kind of application using different services, we need to have some way of connecting them. So now let's look at PaaS services, which actually provide a way of connecting different microservices. Basically, there are different ways to do so. There are cases like where one can use REST API, which is basically synchronous and more well suited for synchronous jobs. Event queue, which is usually focused on large amount of small events. And orchestrator, which is best at handling long-term processes. It can handle complex intermediate logic, and it usually provides a way to trace the process. The main downside is that it's somewhat more expensive compared to others. So if we look at cloud-native orchestrators, usually we get some additional advantages. We have native support for FaaS and CaaS, meaning that this service can start jobs on these services, but it also can resume workflow after the job is finished on Lambda or Fargate, for example. It has central monitoring, where you can basically go to the logs on AWS Lambda or other services, and you can trace any specific job and see what went wrong. And it can scale based on your usage. So when you have basically this kind of orchestrators, you can have a hybrid architecture where you can use different processing nodes, and at the same time you can implement custom logic. You can have parallel execution, you can have branching and loops. So you can increase complexity of your workflow. At the same time, you can keep it flexible and have different job running on different service. So combining everything which I have mentioned before, the serverless approach which we are going to use to implement MLOps patterns will be the following. We will use AWS Lambda for short parallel processing, AWS Batch for heavy and processing and also GPU training jobs, SageMaker for GPU training jobs and distributed training, and Fargate for long-running processing, and basically step functions to organize workflows which would utilize all mentioned services. So let's start with data preprocessing. So option number one is to use basically a combination of SageMaker for heavy processing jobs and using something like FAS for scalable processing in parallel. The idea here is to basically to have small jobs on AWS Lambda, for example, something which parses websites or downloads single image from some data source, and then having some more complex jobs on SageMaker. In somewhat similar way, the same job can be ran on Batch or Fargate. The main difference here is that you need to provide input data and output data as commands to Batch and Fargate. With SageMaker, you don't have to do it. Basically, it will be part of configuration, and it can mount S3 bucket. So where do you know, how do you know if this would work for you? So if you have peak loads, then it will be able to scale automatically. If you have some complex logic, for example, scheduler, or like you want to run something in parallel, then it would work for you really well. And finally, if you want to have multiple programming languages or multiple frameworks, then it would work really well because you can basically separate them in different Docker container images. Where it wouldn't work. So if you want to have a fast synchronous workflow for data processing, then calling AWS Lambda cluster would be easier. Although I would mention that currently step functions also introduced synchronous workflows, but they are limited to 30 seconds. If you have a low CPU RAM consuming workflow and you want to minimize cost, then SQS Kinesis plus AWS Lambda would be a cheaper solution. Here is the repository where you will be able to find templates which you can deploy to your AWS account, which would have AWS step functions with Lambda, Batch, and Fargate. It's basically single line deployment where you can just like run one command and it will deploy everything to your account. So you can test it, but also like it's a very flexible template, so you can update it and use it for your own needs. Next is training. So with training, option one is to use SageMaker. SageMaker is the best when you just need to start and you want to offload a lot of logic to the service, because it will handle high parameter optimization for you, it will handle metrics for you, it will handle model export and input data for you, and it can even run distributed jobs for you as well. That's one of the challenges because Batch cannot run job on multiple machines. Alternatively, you can use Batch. In this case, you need to handle logs metrics by yourself, as well as data input and model export. But at the same time, you will get a cheaper service and you can run more jobs in parallel. And finally, as one of the patterns, you can use external infrastructure. In this case, step functions would run preprocessing jobs which would prepare data and share it. Then your on-premise server would make requests to step functions, get a request, download the data, train the model, upload the model to S3, and then the workflow would continue. Basically, in this case, the pattern would allow you to integrate external hardware into your production infrastructure and basically have a hybrid infrastructure where you have basically public and private cloud. So where would it work? Basically, if you have peak loads and you want to be able to scale, if you have a very rare training jobs and you don't want to maintain cluster, if you have some complex custom logic, as in previous case, or if you want to use external infrastructure or other external services. So where it wouldn't work. So if you want to be able to train models synchronously, which could be the case, in this case, using step functions won't work, though like step functions support synchronous workflows, it just will be more limiting in terms of time. And if you want to maximize training speed, because the services which I mentioned, they need some time to start. And if you have existing cluster, it will start the job right away. So same repository, you can find templates for organizing training pipelines, which will basically have step functions, Lambda, batch, and SageMaker. And finally, inference. With inference, basically, we can start by looking like how usually inference looks like when we want to have a cluster. As you can see, it's somewhat complex if you want to organize deep learning API. The challenge here is that you have multiple interconnected services like load balancer, auto-scaling group, instances themselves, and you want to be able to use spot instances to minimize time, minimize cost. If you want to use serverless deep learning API, then there is a lot less services which you need to deal with. Basically, you just have API gateway plus Lambda. That's all. So alternatively, you can connect Lambda to SQS if you want to process batch jobs, which could be the case like when you just want to process a stream of jobs. Alternatively, you can also connect SQS or API gateway to step functions and run inference using step functions. And there is a reason why it could be useful. Basically, you can organize inference pipeline, and it provides you a way to have a more complex logic, basically by having different models where you can run inference. The main advantage here is that, for example, if you don't want to deploy a new model right away, you can run old and new model, and you can decide whether you want to run them in parallel and make a decision afterwards, like which result do you want to take, or to compare the results. Or you can run 90% of traffic on old model, 10% traffic on the new model, and then increase this ratio. So if you want to organize serverless inference, usually one of the challenges is like where you can keep the model. So, or it used to be, because now you can actually use Docker containers with AWS Lambda, and the limit for containers is 10 gigabytes. So basically you can put almost any model there along with all the frameworks. Different frameworks would have different inference speeds. So usually it makes sense to optimize your model, and something like OpenVino or TFlight or Onyx can provide a significant speed up in terms of both startup time and inference time. So if we compare, let's say, TensorFlow and TFlight with different Lambda configurations, we can see that, for example, if you provide more CPU to Lambda, you may have a better startup time, but you won't get 2 times faster inference. And actually, like with 3 GB RAM, we will have more expensive inference because we will be able to run less amount of predictions for $1. So it's something which you need to keep in mind. So basically, when you want to balance speed and cost, so sometimes you can improve one, but decrease another. There are certain life hacks for serverless inference in terms of what you can do. Basically, usually it only works like if you want to package your model, and if you use Docker images, you don't need to optimize model really well because you have 10 gigabyte limit. So where it would work, if you have some pet project, or if you want to build some simple MVP for your project or startup to get very early customer feedback, then it's a very simple architecture, which is also very scalable, so you can use it in production right away. Alternatively, if you have some very simple model, then this architecture can help to reduce cost because you won't have any idle time. And if you have peak loads, then it would work also very well because it will be able to scale based on your load. Where it wouldn't work, If you have to handle real-time response or your model requires a lot of data or processing power, which is not a case as much because now we have 6 vCPUs and 10 gigabyte RAM and 10 gigabyte container image size. But also, like, if you want to handle extremely large amount of requests, more than 10 million requests, at this point, cluster may be a better solution because it will be somewhat cheaper per request, and it is more customizable, and you can customize your instance for your model. So there are 2 repositories which contains packages for AWS Lambda and Google Cloud Functions, with focus on different machine learning and deep learning frameworks, like TensorFlow, like Scikit-learn, OpenCV, and Spacey. So feel free to check. It's MIT license, so you can freely use it for your projects. So in summary, cloud native orchestrators are very convenient, and you can use them to construct deep learning pipelines for data processing, training, and inference. There are a lot of services which you can use, and basically it depends on the context which one you should use. So basically keep in mind that in some contexts you can start with one service, but then eventually just migrate to another, because like they all work with Docker containers in some way. And finally, there is no upfront costs, and you can easily deploy this kind of workflows when you are reusing existing templates. So you can even start using it for your research project when you want to start running some of the jobs in the cloud. So thank you very much for your time. And here are the links to the repositories which I've mentioned, and link to my website where you can check some online courses which I did, as well as links to my blog posts. So if you have any questions, I would be happy to answer them. Great question. Have you compared these techniques to running on EKS with something like Kubeflow? So with EKS, basically, it will be similar in terms of pricing with AWS Batch, because EKS and Batch are using the same instances. So with EKS, it will be somewhat more expensive in terms of that you will need to pay for EKS as well. AWS Batch is basically free, because AWS Batch, you don't pay for Batch itself, you only pay for instances. So if you compare Batch and EKS, it's like, and the EKS with Kubeflow, it will be the same way. The difference would be that EKS plus Kubeflow is a lot more customizable. I mentioned, like with Batch, Batch manages how it starts and terminates instances based on your job queue, and with and you cannot control this logic. And sometimes maybe it's not desirable. It's not a desirable way. So with EKS and Kubeflow, you can customize it more, but with AWS Batch, it's a lot easier to start. Okay, it looks like we may have an additional 1 or 2 minutes. Actually, let me answer another question. While comparing GKA and EKS, it looks like GKA is better in terms of its logic of auto-handling failure of nodes, whereas EKS has that logic still in development. Is this true? If so, is it because Google owns Kubernetes? It's hard to say, because like I'm not like very familiar with EKS and GKA. Basically, they both are somewhat like branches of Kubernetes. Basically, they're not like 100% the same implementation, so they have some differences. And I would say that that's why it's hard to implement failure of nodes, because like some of this logic exists on Kubernetes level. So that's why sometimes you may want to have some orchestrator with logic of retrying your job. So for example, with step functions, the thing you can have, like you can have a timeout for your job. So if it, for example, failed to start, it can you can retry it, or you can fail your workflow and send a notification. So we have one additional minute, and I just want to show you a quick demo. So I have deployed a simple deep learning training workflow using step functions and AWS Batch. So here's how I just needed to run serverless deploy, and it deployed everything for me. So I just want to show, and I ran some jobs. So I want just to show you how it looks. So when you go into a specific job, you can see the whole execution graph. And within execution graph, you can see like parallel jobs, and you can see input and output of each step. With batch, you can see like you can see successful jobs. And in CloudWatch, you can actually see the logs of each batch job. So you can see here the logs for your training. Basically, here how it looks like. So this is the repository which I mentioned. Here in AWS Deep Learning Training, you can see that there are files which define your Docker container and your serverless configuration. And here is how template looks like. You just need to define lambdas. Here you define step functions graph. And finally, you define resources for your infrastructure. Okay, thank you very much for your time. And the links to the slides is in the chat.
Rustem, thank you so much. I really appreciate that. And it's great to have you join to share all this work with us. It's really great. Yeah, I hope everybody enjoyed it. And we will send out the slides to everybody. And the videos, once we're done editing, will be sent as well. So Rustem, again, thank you so much. I hope you enjoyed it.
Thank you, Dave. Thank you very much for organizing the
Most
conference.
welcome. Okay, take care.